This Mechatronic device is a self-watering houseplant. The motivation behind this project was to develop a system that could tend to common houseplants. It works similar to an alarm clock, where the user defines times or cycles that they would like to water their plant. When the cycle is ready to commence, an actuator dispenses water, which is then delivered to the plant via a tube by the effects of gravity. Our system contains an LCD display which will prompt the user to set up a cycle in addition to providing them information. An LED is used to show the status of the water level inside of the cooler, and 3 of the buttons allow the user to interact with the settings. Of course, we have our Arduino, which is the brain behind this entire system. In my hand is a Wi-Fi module, which allows the user to monitor their plant via an app even when they are away from home. And below the Arduino is our real-time clock, which keeps track of the time. Here's our motor driver, which is the muscles behind the system, and it is powered and supplied by 2 9-volt batteries. In addition, you can see the water level sensor that is through the housing. This determines the water level as well. And outside of the system, we have our moisture level sensor, which is in the pot of the plant, along with our stepper motor. Here we are uploading the code. Generally, it takes about a minute in order for the system to start up and connect to the Wi-Fi. Here we will demonstrate a remote setup via the app. First, we must enter the current time. Once the current time is entered, the user defines how many cycles they would like to run. After the number of cycles has been defined, the user enters in various times throughout the day when they would like their plant to be watered. Lastly, the user enters in how many cups of water they would like dispensed on each cycle. Once the setup is complete, the system enters into an idle state where it begins to display the time. It will remain idle until it is interrupted, in other words, when the watering time has been reached. One thing to note here is that the LED is currently red. This is because the water level sensor is not sensing any water, and thus the cooler is deemed to be low on water, where the red color indicates to the user that they should refill soon. Finally, the watering time has been reached and a nice message displays to the user. Once the watering time has been reached, the actuator arm of the stepper motor rotates and pushes the plunger of the spout inward. This allows for water to flow through, which is funneled and sent to the tube below. Once enough water has been dispensed, the motor rotates in the opposite direction, which allows the plunger to be pulled back into a closed position via the fishing line that connects the two. Information to the user is displayed in periods of about 1 minute, more or less in between cycles, and after watering has been achieved. Moisture level of the soil is displayed to the user, that way they know if they are watering too often or not enough. In this case, the moisture level is beyond the threshold for this plant, so the watering cycle is skipped to prevent overwatering. Next, the display shares the number of times the plant has been watered. This will depend on the number of cycles set by the user, and also if any cycles have been skipped, which is why in this case, it is telling us it has been watered 0 times. Finally, the water level reading is provided to the user, that way they have a more accurate reading of how much water is really left inside of the cooler. Now time for a manual setup, using the buttons, which are located on the back of the system near the LCD and RGB LED. The right button doubles as a plus to increase or to change the hour of the time. The middle one doubles as a minus to decrease or to change the minute of the time. The left one being the set button, which will save the settings or return the user to setup mode after the system has been in idle mode in case they need to adjust their settings. Notice here the LED is green. This indicates to the user that the water level sensor reads enough water, meaning that the cooler is full with water and no refilling is required. Again, once the cycle time has been reached, the spout is actuated via the stepper motor, which delivers water to the plant below. The actuator arm pulls back in order to close the spout. Now let's take a closer look at the code that controls this system. Shown here is the beginning of our void loop function. Because our code is rather lengthy, only a switch statement was employed in this function. Other features were separated into their own functions in order to make a more efficient and less repetitive code. For example, like the update RGB function, which will change the color of the LED depending on how much water is in the cooler. The main loop controls our setup mode. We start out at case 1 after the Wi-Fi has been connected and communication has been reached between the system and the app. We prompt the user to enter in the current time. Depending on which button is pressed, we call the according function to increase the hour or minute on the clock. If the set button is pressed, the real-time clock is calibrated, and then we move on to state 2. Note, delays are added in order to prevent unwanted readings from the buttons when they are pushed. After we have set, we can move on to case 2. Here in case 2, we want to know how many cycles the user intends on running throughout the day. In order to look more aesthetically pleasing, we censor the text on the LCD display. Depending on which button is pressed, the number of cycles can either be increased or decreased through these simple if statements, although we do restrict the user to a max of 3 cycles and a minimum of 0 cycles. Again, we add delays throughout in order to prevent unwanted readings. If the set button is pressed, we know that we can move on to case 3. In case 3, we determine what times the user wants to water their plant. We call 2 of our functions, which display the times entered. These times are dependent on the number of cycles. As the more cycles set, the more watering time is necessary, and vice versa. In both instances of the hour button or minute button being pressed, we update the array values. Upon pressing set, we double check if there are any more cycles to set. This is done as a precaution, as we know the indexing of the cycle number array starts at 0. However, if all things check out, we can move on to state 4. Again, delays are added throughout to prevent unwanted readings. In state 4, we set the amount of water to use during each cycle. We first prompt the user and censor the text to look neat, then we wait to see which buttons are being pressed. If the plus button is pressed, the desired amount of water increases by 1/4 of a cup, and if the minus button is pressed, the desired amount of water decreases by 1/4 of a cup. We limit the user with a maximum amount of water being 2 cups and a minimum amount of water being 0 cups, with each increment being 1/4 of a cup. Once the user hits set, the LCD lets them know that the setup has been complete, then it clears. We can now move on to state 5. State 5 is an idle state. We first employ a flag in order to check if the current time is a watering time. If the watering time has been reached and we haven't already watered, we enter state 6. We reset the timer for the displays, the state of the display, and both flags. We then mark the hour and minute to update the flag variables and call our function which moves the stepper motor inward, which consequently pushes the plunger located within the spout of the cooler. If at any point during the idle state the set button is pressed, we return back to state 1 and restart the setup mode. In state 6, we finally water the plant. Because of sensor restrictions, we instead went with a time-based approach, discovering that approximately 1 cup of water flows through our system after 5.5 seconds have passed. We hold the motor in the press position for however long required before rotating the motor in the opposite direction, which is done by calling our unpressed spout function. The LCD prints a message to the user, and then it returns to the idle state to continue checking for the next watering time. We then update all of our old values at the end of the loop and initiate the blink timer, which sends data to the app. For our project, we used Blink Legacy, which we found was an app that paired very well with Arduino. Here we take a closer look at the display info function. Because our system is an idle for a majority of the time, this function is extremely important as we want to share with the user information about their plant by displaying information to the LCD. The important variables to note here are flag 0 and flag 1. If flag 0 is raised, we know that it is watering time, but flag 1 can also be raised here. While maybe tricky, this if statement allows us to prevent a double dip at the watering time by ensuring the if statement is only executed when the timer value is less than 2000 and the OR operation is true. First, we display the current time by calling one of our functions. We then increment the time. If we increment the time so that we reach 2000, we leave the loop as the time limit has been reached, and we then continue to the next state. The timer is reset, as is the LCD. Then, we display the moisture level to the user by calling our display moist level function. This function returns the moisture level as a percent, which was derived by accumulating 30 readings from our sensor via a for loop, finding the average of those readings, and then calculating the percent based on the maximum and minimum readings we were able to obtain from our sensor during testing. In case 2, we follow a very similar process as we did with case 1. We continue incrementing the timer, and once it has reached the time limit, we then move on to the next state. We reset our timer at that point, then display to the user how many times their plant has been watered today by employing the counter variable that we incorporated earlier into the code as a global variable. Again, in case 3, we follow a very similar process, only this time we display the water level to the user. By calling our display water level function, which is similar and essentially uses the same logic as our moisture level function. Case 4 is similar to the previous cases, except here we want to update flag 0 just in case the plant needs to be watered. But the same logic applies. Once we leave the loop after the time limit has been reached, we reset the timer to 0, clear the LCD, and return to state 1 in order to repeat the process and continue displaying information to the user, which could be useful as it does indicate the health of their plant. Given the time and resources, we would have loved to implement different changes to make the system more efficient. Nonetheless, we did enjoy completing this project and we hope to build upon it from here.